Two black holes are racing toward each other in complete darkness. No light, no warning, no explosion you can see coming. And then, boom! Not a flash, not a fireball, but a ripple in reality itself, so powerful it shakes the fabric of the universe. Here's the part that sounds impossible. When black holes collide, the most violent event in the cosmos doesn't produce light. It produces gravity. Let that sink in. Black holes are objects so dense that not even light can escape their gravity. They form when massive stars collapse at the end of their lives. What's left behind is a region where mass is crushed into an incredibly small space, creating an event horizon, the boundary beyond which nothing returns. Now imagine two of these monsters locked in orbit. They don't just smash into each other randomly. First, they dance. As they orbit, they lose energy, not through friction, not through fire, but by emitting gravitational waves. These are ripples in space-time itself, predicted by Albert Einstein in 1916 as part of his theory of general relativity. For nearly 100 years, we had no proof they existed. Until 2015. On September 14, 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected something extraordinary. Two black holes, about 36 and 29 times the mass of our Sun, had collided roughly 1.3 billion light-years away. In their final fraction of a second, they merged into a single black hole about 62 times the Sun's mass. If you're good at math, you'll notice something strange. 36 plus 29 equals 65. But the final black hole was only 62 solar masses. Where did the other 3 suns' worth of mass go? They were converted directly into energy. In less than a second, about 3 times the mass of our Sun was transformed into pure energy in the form of gravitational waves. For that brief moment, the collision released more power than all the stars in the observable universe combined. And we didn't see it. We felt it. By the time those waves reached Earth, they stretched and squeezed space by a fraction of the width of a proton. LIGO detected that minuscule distortion using laser beams fired down 4-kilometer-long tunnels. The change was smaller than 1/10,000th the diameter of a proton. That detection changed astronomy forever. But here's where it gets even more intense. As two black holes spiral closer, they accelerate to astonishing speeds, approaching half the speed of light before merging. Their orbital period shrinks from seconds to milliseconds. The gravitational waves they emit increase in frequency and amplitude, creating what scientists call a chirp signal. If you convert those waves into sound, it literally sounds like a rising chirp. That chirp is the sound of space-time tearing and reshaping itself. And then comes the merger. At the moment of collision, their event horizons fuse. There is no solid surface, no impact in the traditional sense. It's not like two planets colliding. Instead, space-time itself becomes violently distorted. The newly formed black hole is highly unstable at first. It wobbles and vibrates, settling into a stable shape in a phase called the ring down. Think of striking a bell. The merger is the strike. The ring down is the fading tone. Except this bell is warped space-time. Now here's something controversial that surprises many people. Black hole collisions are not rare cosmic accidents. They are happening all the time across the universe. Since 2015, LIGO, along with its European partner Virgo and Japan's Kagra detector, have identified dozens of black hole mergers. Some involve black holes much larger than we expected. In 2020, scientists announced the detection of GW190521, a merger between two black holes about 85 and 66 times the mass of the Sun, located roughly 7 billion light-years away. The final black hole was about 142 solar masses, placing it in the category of an intermediate mass black hole, something astronomers had long searched for. And once again, several solar masses were converted directly into gravitational wave energy. But let's interrupt something most people assume. Do black holes create giant explosions when they collide? Usually no. If the black holes are isolated, meaning there's no surrounding gas or matter. The merger is completely dark. No flash, no fireball, just gravitational waves passing silently through the cosmos. However, if the collision happens in a region rich with gas, like the disk of a supermassive black hole, there's a possibility of electromagnetic signals, light, X-rays, maybe even gamma rays. Scientists are actively investigating such scenarios, but gravitational waves remain the primary signal. Another misconception: do black holes swallow everything nearby during a merger? Also no. Despite their terrifying reputation, black holes don't act like cosmic vacuum cleaners. If our sun were magically replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. Gravity depends on mass, not on whether that mass is a star or a black hole. So when two black holes merge, they don't suddenly start devouring the universe. Their gravitational influence is determined by their mass and distance, just like any other object. Now here's where things get even more fascinating. Gravitational waves travel at the speed of light. We confirmed this in 2017 when detectors observed a neutron star collision, GW 170817, along with light from the same event. The gravitational waves and light arrived almost simultaneously after traveling 130 million light-years. That confirmed Einstein was right again. Every time we detect a black hole merger, we're not just witnessing destruction. We're opening a new way of observing the universe. Traditional astronomy relies on light, visible, radio, infrared, X-ray. But black hole mergers are often invisible in light. Gravitational wave astronomy allows us to hear events we cannot see. It's like humanity suddenly developed a new sense. And we're just getting started. Future observatories like the space-based LISA mission, planned by the European Space Agency, aim to detect gravitational waves from even larger systems, including supermassive black holes millions of times the sun's mass. Those mergers will unfold over months or years, not milliseconds, giving us an entirely different window into cosmic evolution. Because here's the deeper truth: black hole collisions shape galaxies. At the centers of most large galaxies, including our Milky Way, sit supermassive black holes. When galaxies merge, their central black holes are expected to eventually collide as well. These titanic events help determine the growth and structure of galaxies over billions of years. So when two black holes collide, it's not just a dramatic cosmic event. It's part of the story of how structure forms in the universe. And yet, even with all this knowledge, we still don't know everything. What happens at the exact center during the merger? Does the singularity behave as our equations predict? Could extreme mergers reveal cracks in general relativity? So far, every observation agrees with Einstein's theory. But scientists are watching closely for any deviation. Because if gravity behaves even slightly differently under these extreme conditions, it could point toward new physics, perhaps even a path toward unifying gravity with quantum mechanics. So the next time you look up at the night sky, remember this: somewhere out there, two invisible giants may be spiraling together, warping space-time, releasing unimaginable energy, not in light, but in gravity. And right now, Earth is constantly being washed by ancient gravitational waves from collisions billions of years old. We are living inside a vibrating universe. If this expanded your mind even a little, follow for more deep dives into the most extreme events in the cosmos. The universe is far stranger and far more beautiful than we were ever taught. Now let me ask you this: if gravitational waves let us hear the universe for the first time, what do you think we'll discover as our detectors become 1,000 times more sensitive?